Good morning, everybody. I know we usually start with the do now, but chapter 6 is kind of big and I want to make sure that there's enough time for us to get through everything and for you to ask your questions. Normally we do exam review up front if there's an exam this week, but instead of doing that, I've posted a practice exam on Blackboard. It's posted in the course content folder. You should see practice exam 2. You do not need Respondus Lockdown Browser to take it. It's about 13 questions and it covers all the chapters 4 through 6. You'll get to see whether or not your answer is correct and you'll get to see what the correct answer is. So that should help you with your studying. Are there any burning questions from chapter 5? Or any questions about the upcoming exam, like logistics? Not how many questions is it, but, how to take the exam. If you don't have any questions, just let me know. Say you're ready, and we'll start chapter 6. Okay, so I have not set a time limit, but you should be able to complete the exam in approximately an hour to an hour and a half. And the exam will be available on Wednesday, and it will close at 11:59 p.m. Eastern Time on Friday. You're welcome. You're very welcome. Just out of curiosity, how many of us were able to watch at least some of the chapter 6 lectures for this week? Because I posted 2 videos, it would have been too long. If you're just joining us, we are not doing exam review during class because we do not have time. So there is a practice exam posted already. I'm sure I'm probably going to get that question again. So y'all help me out if somebody posts a question about exam, like if someone asks a question about exam review, just let them know there's a practice exam. I already posted an announcement to Blackboard as well, but I'll send another one after class. Your actual exam 2 is opening on Wednesday morning. So hopefully you got a chance to at least take in some of the chapter 6 lectures. It's not hard, it's just remembering stuff. So for exam 2, you will get a periodic table and you will also get the common polyatomic ions chart, which you will see in this lecture. So I'll point that out. But those are the 2 reference pieces that you get along with your exam. Make sure you print those out before you get started. I'll go over all of this again at the end, so don't worry. Now we're going to get started with chapter 6. The first section is talking about ions. So we're talking about transferring electrons around. In general, atoms are going to lose, gain, or share electrons to get an octet of 8 valence electrons. So this part right here, that's the octet rule. So when the octet rule is mentioned, that's what we're talking about. Atoms are going to lose, gain, or share electrons to acquire an octet of 8 valence electrons. We've got 2 different types of bonds that we can talk about here. We've got ionic bonds and covalent bonds. For an ionic bond, you have a metal and a nonmetal, and you're transferring electrons from the metal to the nonmetal so that you have ions. The positive ion is a cation, and the negative ion is an anion. You may have heard that before in high school chemistry. With a covalent bond, you're sharing electrons. You have 2 nonmetals that get close enough together to where they can share electrons and fill their valence electrons. So that's ionic versus covalent. Are we good on that? Okay. Now we're going to talk about ions. We're going to focus on positive ions first. And remember, positive ions lose electrons. The other name for a positive ion is a cation. And when we talk about positive ions, we're pretty much talking about metals, which is most of the periodic table. We'll use sodium as an example. This is the same example I used in the YouTube video, but I'm going to go over it a little bit more briefly. So if we look at sodium, it's in group 1A. It has 11 electrons and 11 protons. We know that it has that many because the atomic number is 11. So atomic number equals the number of protons. And in a neutral atom, protons equals electrons. If we were to look at the electron configuration for sodium, which is down here, I just underlined it, the valence electrons are going to be in that outermost shell. We're talking about the S and P electrons. So we're going to talk about the 3s electrons, okay? Those are in the valence shell. When sodium loses that 1 electron, it goes from having 11 electrons to 10 electrons. Now we've got more protons than electrons. So we have a positive charge. Does that make sense to everybody about how you form a positive ion? Before we get to the negative ions, I want to ask you, if having more protons than electrons gives you a positive charge, what would you need more of to have a negative charge? More protons than electrons or more electrons than protons? Right. You need more electrons. So if we have chlorine, for example, and we start with a neutral atom, you've got 17 electrons and 17 protons. Chlorine is a nonmetal, and that's what our anions are. They're nonmetals. And they're going to gain electrons to achieve that full octet. So instead of starting We're going to start with 17 electrons in chlorine, and it's going to gain an electron so that it now has 18. So we've got more electrons than protons, and that gives us a negative charge. Also, take note that now chlorine has the same number of valence electrons as argon. So if we were to write the electron configuration instead of the full configuration, we wrote the condensed or abbreviated, it would look like argon. So we good on that? That's negative ions and positive ions. So let's do a learning check. I want you guys to go through this for the element nitrogen, just like I had on the other pages. You want to figure out, is it a metal or a nonmetal? How many valence electrons it has, which that is a review from chapter 5. And then how many electrons it has to lose or gain, and then write its symbol and ionic charge. So I'll give you 2 minutes to give that a shot. Are we ready, or do we need more time? I'll give you another minute. And if you want to put your answers in the chat, you can. We can also just go letter by letter and put it in that way. So is nitrogen a metal or a nonmetal? Ayana, I see your answer, so you don't have to answer again. Right, nitrogen is a nonmetal. It's over to the far right of the periodic table, and that's the corner where the nonmetals hang out. How many valence electrons does nitrogen have? Yep, it's got 5 valence electrons. And if you don't remember how to figure that out, the group number is equal to the number of valence electrons. But it has to be the one that has the A after it. So nitrogen is in 5A, so it's got 5 valence electrons. How many electrons must nitrogen lose or gain? So is it going to gain or lose, and how many? It's going to gain because it's a nonmetal. And with the octet rule, we know it's going to try to fill up to 8. The difference between 8 and 5 is 3. So it's going to gain 3 electrons. Yeah, there's a hand. Yes. So we know we're going to gain 3. Now we've got to write the symbol. You can't really do that well in the chat, so I'll write it here. So that's going to be N3 minus. And we didn't talk about naming. I was going to do that here. So to name this ion, it's an anion. You're going to start with the name of the element, which is nitrogen. We want to keep the first syllable and get rid of everything else. The first syllable is kind of the nitra. You get rid of everything else and replace it with IDE. So this is called the nitride ion. And to test your understanding, let's say that we had O2 minus, which comes from oxygen. How would you name this anion? It's the same rules as we did before. You're going to keep the ox, which is the first syllable. Get rid of everything else and replace it with IDE. So that's the oxide ion. You don't want to use any prefixes here because that's for the molecular compounds. We're talking about ionic compounds. So does everyone see the rule for naming? This is just for anions. Okay. Let's go through and do another one. This time you're going to think about the element barium and answer the same questions. So I'll give you 4 minutes since that seemed like a good amount of time. I'll give you 4 minutes and then we'll go through letter by letter and put our answers in. Let's get started. Is barium a metal or a nonmetal? It's a metal. How many valence electrons does barium have? It's got 2, right? So it's in group 2A. That means 2 valence electrons. Are we going to lose or gain those electrons? We're going to lose 2. So it's a metal. That means we're going to lose our valence electrons. Yes. Yes. So if you lose those 2 on the outside, then what's underneath is a full octet. Okay. Now we need to write the symbol and the name. The symbol, since we're losing electrons, is going to be barium 2+. The way that we name it is pretty simple. You write the name of the element, in this case it's barium, followed by the word ion. Doesn't get any simpler than that. So when we're talking about a metal, at least for now, we're just going to name it with the element name followed by ion. So if you had Mg2+, it would be the magnesium ion. This is for naming cations, specifically the representative metals. So all that means is the metals that are in group 1A, 2A, and 3A. The other metals we're going to address a little bit later on because we have to give a little bit more detail with those. So is everyone good on this? This is just practice for positive and negative ions. How we feel about those. Alrighty. Then let's keep pressing forward. Now we've got a foundation. We've talked about ions. Now we can build up to ionic compounds. We're going to be writing formulas and writing names. In a chemical formula, you want to make sure that one, you have the lowest whole number ratio of the atoms or ions involved. So we all know table salt, NaCl. You wouldn't write it as Na5Cl5. No. That ratio is 1:1. So you should write it as 1 atom of sodium and 1 of chlorine. So that's what that means, the lowest whole number ratio. The sum of the ionic charges in the formula has to equal 0. We were just writing out the charges for different ions. For sodium, we know it has 1 valence electron and it's going to lose that valence electron. So its ion is Na+. Chlorine has 7 electrons in its valence shell and it's going to gain 1. So its charge is -1. +1 plus a -1 gives us 0. So if you add up the total charges for the whole formula, it should be 0. Is that clear? We're going to make sure to do some practice too. But this idea of having the 0 charge total is key to writing chemical formulas. So I'm going to go through, yeah, there's a question. No, it means so if I have +1, then I'm also going to have -1. So they're equal but opposite is another way to say it. Or if I have, let's see, magnesium oxide, we know that magnesium is Mg2+, and oxide, that's 2-. So it would be +2 plus a -2 equals 0. Okay, you're welcome. So I'm going to go through and do the first one for you. And then the other two I want you to try. I want you to figure out the correct formula for the ionic compounds based on the idea that the formula has to have a net charge of 0. So the total positive equals the total negative. For the first one, we've got sodium, and it's +1. And oxygen is 2-. Well, if I just had one of those and one of those, it would be +1 plus a -2. We'd come out as -1. So we've got to have more than one of something. Should I have more sodium ions, or do I need to add more oxide ions? I need to add more sodium. Since we came out negative, that means we've got a bigger negative charge than we do a positive charge. So instead of one sodium atom or ion, we're going to have two. So that's B. I want you to complete 2 and 3 the same way. I'll give you a couple of minutes to do that. What do we get for number 2? I agree. You should get A. We've got aluminum ion, and that's the 3+. And then we've got the chloride ion, which is only -1. If we just had one of each, we'd have a +2 charge. We can't do that. So you need to add more of that negative ion to balance it out. You need 2 more. The other way that you can do this, which I showed this in the video, if you know your ions, yeah, there's a hand. You would be told. But, yeah, normally those are involved in molecular compounds, not really ionic compounds. So you wouldn't have to worry about that. You're welcome. The other way to figure this out is to use the cross method. So you take the number from the charge of the positive ion and write that as the subscript for the negative ion. And then you do the same in the reverse. So remember, there's an implied 1 here when we have just a negative or a positive. But we don't write the 1 when we write the chemical formula. So it would simply be AlCl3. So that's the cross method. You don't have to do it that way. But if it's confusing for you any other way, this way will always work. What do we get for number 3? C. And that gives us 3 times a +2 plus 2 times that -3, which is 0. Whoop. Are there any other questions on writing formulas for ionic compounds? I'm going to take that as a no. So let's do some more. We're able to choose the chemical formulas just based on the positive and negative ions and making sure that the formula overall had a charge of 0. So let's do some more practice with that and writing formulas. Let's learn how to name these. So we've learned how to name the ions, the negative ions and the positive ions. Now we need to put those together. Whenever you're naming an ionic compound, the metal is written first. So we'll use our example that we came up with before, AlCl3. That's one of our ionic compounds from our last learning check. So to name this compound, the metal would be written first. And the metal is always first in the formula too. That's aluminum. If the metal is a transition metal, then you have to include the ionic charge. And we're going to talk about how we figure that out in just a minute. For our case, for this example, aluminum is a group 3A metal. It's not a transition metal, so we don't have to worry about its ionic charge. The next word that comes in the ionic compound name is named for the nonmetal. Just like we did with naming the negative ion, you're going to take the first syllable of the element. We have chlorine, so that's going to be chlor. And then you add IDE. So that word is aluminum chloride. That's how we would name that compound. So let's do another one that's simple. Let's name the compound that we just did from letter C. I'll give you a minute to think about it, and you can put your answer in the chat. Thankfully, this is not a spelling exam. It's a multiple choice exam for exam 2. So if your spelling is a little off, that's okay, as long as you can pick the right one. First word's going to be magnesium. Not a transition metal, so we just write the name of the element. We take the first syllable of the nonmetal and add IDE. Magnesium nitride. Questions about that before we move on, because we're going to talk about transition metals next. Go for it. What's your question? No. The only time that you might see a metalloid is maybe boron, but that's for a molecular compound, not ionic. No, you're mixing ionic compounds and molecular compounds. We haven't gotten to molecular compounds yet. It's okay. It's okay. It's a lot of rules. It's a lot of rules. A lot of stuff to keep separate. I've had like decades to remember this. So you've had a few days. It's all right. You're welcome. So there are some metals that have a variable charge. The D block, which is kind of that center portion that's filling the D orbital, they're the transition metals. And they can have more than one positive charge. There are some exceptions, though. The exceptions being zinc, cadmium, and silver. They only form one charge. All the others suspect them to be able to form multiple charges. So if you see copper, iron, and even some of the larger metals that are not transition metals, like lead and tin, they can form multiple ionic charges. So you can have lead 2 plus or 4 plus. You can have iron 2 plus or 3 plus. And it really matters which one you have because the chemical formula is different and they have different properties. So when we're writing names with metals that have a variable charge, you have to include the Roman numeral that's equal to the ion charge. I'm going to give you all the Roman numerals up to 6. You shouldn't need anything higher than that. Probably won't need anything bigger than 4, but I just gave you a couple of extra. So make sure you know your Roman numerals and you recognize when you need to use them. So when you see a compound that has zinc, cadmium, or silver, don't use Roman numeral. You may see this referenced as the stock system. That's what it's called when you're using a Roman numeral. So is that clear? This is just for transition metals, excluding our exceptions. So let's do a little bit of practice with this. Because when we're writing the name from the compound, we can't just straight up write the name. We have to figure out what the charge is on that transition metal. So we'll take one of our examples from this table and break down how we got the name. Let's do this one. It's copper 1 phosphide. Copper we recognize is a transition metal, which I abbreviate TM. So we can write out copper, but we have no idea what its charge is right now. How do you think we can figure it out? Is we do have a clue as to what the charge is. We know what the anion is. If we know what that is, then we can figure out the total negative charge, right? And we know that our total positive charge has to be equal to that. So for phosphorus, what is the charge going to be on the phosphide ion? That's the number of valence electrons. It has 5 valence electrons. The charge on the ion is going to be the number of electrons that it gains. The phosphide ion has a charge of 3 minus. So we know that our negative side is -3. So we have to have a +3 total for our positive charge. We have 3 copper ions. So that means that we have to divide this charge by 3. So we get 1. Each copper ion has a charge of 1. Then you name the anion, which is phosphide. But the key is figuring out that copper piece. Does anyone need me to go over that again? Okay. Let me get a different color here. We have this formula, Cu3P. Copper is a transition metal, so we know we're going to have to use the stock system or put that Roman numeral because it can have multiple ionic charges. The way we can figure out the charge on the copper is by looking at the anion, or the negative part of the ionic compound. It's a phosphide ion, and we figured out that its charge is -3. We know that's going to be our total negative charge. And for this compound to have a neutral charge, or a charge of 0, the total positive has to be +3. Now, if all we had was just one copper ion, we'd stop there and say, oh, the charge is 3+. But we have 3 copper ions because of this subscript here. So that means that our total positive charge you have to divide it by the number of positive ions that you have. So in this case, it's +3 divided by 3, which gives us +1. So each of those copper ions has a +1 charge. And we put a 1 as a Roman numeral right behind the copper. Does that help? We're going to do some practice with this too. So it helps sometimes to just kind of work through another example. So I'm going to work through the first one with you, see how you feel, and then I'll let you work through a couple on your own. All of these are not going to be transition metals. They're not all transition metals. So we're going to do one that is. So A has a transition metal in it. It's got iron. We know that our first word is going to be iron, but we have no idea what the charge is yet. We've got O for our negative ion. What's the charge on the oxide ion? It's 2-. So oxygen is in group 6A. So to figure out that charge, you take that group number, subtract 8, and that gives you -2. I know I covered that in the video, but I didn't explicitly say it here. But the number of electrons that you gain tells you the charge of your anion. So we know that we've got O2 minus, and this subscript of 3 tells us that we have 3 of them. So that means we've got 3 times -2 to give us a total negative charge of -6. That means our 2 iron atoms times its charge must give us a +6. So what charge does the iron have to have? It's got to have a charge of +3. Then we finish naming with the word oxide. So I want you to try the remaining 3, B, C, and D. Again, they don't all require the use of that Roman numeral. So make sure that you only use it for the ones that you do need it. I'll give you 4 minutes to start. And since we have so much material, we'll probably just go over it in that time. So 4 minutes, and then we'll go over it. Let's get started with letter B. Do we have a name? I agree with that. It's aluminum oxide. Aluminum is not a transition metal. So we do not need to use the stock system. You just name that first element, and then you name the negative ion. What about C? It should just be magnesium chloride. Because again, magnesium is not a transition metal. What about D? So tin is it's not a transition metal in the D block sense, but tin and lead are 2 of the metals that can also have multiple ionic charges. So you need to specify using that Roman numeral. So that's tin 4 oxide. You've got the oxide, and there's 2 of them, for a -4 charge overall. That means that you have to have a +4 for the tin. And there's only one tin atom. So it's just going to be a +4 charge. Yes. What's your question? Sure. So tin is not a transition metal in the sense of being a part of the D block, but it can have multiple ionic charges. So we have to use a Roman numeral to designate its charge. To figure out the charge, we look at the anion. We've got oxide, and there are 2 of them. We know that the charge on the oxide ion is -2. For our total negative charge, it's going to be -4. Since the whole compound has to have a total charge of 0, our total positive charge has to be +4. There's only one tin, so if you divide by the number of positive atoms, you're going to get +4 for the charge. What's your question? We're talking about negative charge. 2 times -2 is always going to give you -4. Negative times a positive is always a negative. Nope. No problem. So we have to put a 4 as a Roman numeral in the parentheses. So we get tin 4 oxide. So don't forget, tin and lead also have multiple charges. So whenever you see an ionic compound using one of those, know that you need to use the stock system. Are we clear on that? Can we move on? Now let's try writing the formula from the name. I'm going to do the first one for you. We've got nickel 2 sulfide. That 2 as a Roman numeral in the parentheses tells us what the charge is. The symbol for nickel is Ni, and its charge is 2+. Now we have to figure out the sulfide ion. The SULF comes from sulfur. So you have to recognize the first syllable and match it to the element. Sulfur is in group 6A. So like oxygen, it will also have a charge of 2-. If we put 1 ion of the nickel and 1 of the sulfur together, we'd have a +2 plus a -2, which gives us 0. That means that we can write NiS as the chemical formula. Does that make sense for everybody? And if it doesn't, that's okay. You can say no. Just ask me to run that back and I'll happily go over it again. Go ahead with your question. Because it has it in parentheses next to it. Nickel is a transition metal. Yeah. So I can go over it again. I got a request for that. So we're starting off by looking at the name, nickel 2 sulfide. The first part of the name is always going to be the metal. So our metal here is nickel. It's a transition metal, and we know this because right after it as a Roman numeral, we've got 2. That Roman numeral tells us the charge. So our metal ion is going to be nickel 2 plus. Now we've got to deal with the anion, which is the second word, sulfide. The first syllable is sulf, S-U-L-F. You have to match that to a non-metal on the periodic table. The only thing you can match it to is sulfur. Now that we know we've got sulfur here, we can figure out its charge. Sulfur is in group 6A. So the charge is going to be 6 minus 8, which is equal to -2. So we know that we've got the sulfide ion, which is S2 minus. If you put one nickel ion and one sulfur ion together, you've got a balance. You've got a 0 charge for your chemical formula. So that's how you know that you're right. So our formula is NiS. I want you to try B and C. It's a little bit more difficult to write chemical formulas in the chat, so don't worry about writing your answers in the chat, but I'll just give you a couple of minutes and then I'll show the work for how to get it. And you can check your answers, and I'll check in to see how you did. So I'll give you 2 minutes to get started, and we'll go from there. I'm going to start working on these problems so you can check your work against what I'm doing. So I'll do B in a different color so you can see. So B will be in green. We've got zinc chloride. Now zinc is a transition metal, but it's only got one ionic charge. Zinc is always 2 plus. So that's one of those things you will have to commit to memory. The chloride ion comes from chlorine. That's Cl. It's in group 7A. So the charge for this anion is going to be 7 minus 8, which is -1. To balance this out, we're going to have 2 chloride ions. So our formula is ZnCl2. How do we feel about that one? So I have practice for you. I can't remember if I posted it or not, but I have chapter 6 naming and writing chemical formulas. So I will check and see if I posted that already. I think I did, and the answer key. But the key with the naming and writing chemical formulas is practice. Once you practice, then certain things will just kind of be ingrained in your mind, and you'll be good to go. So the third one I will do in blue. Iron 3 oxide. That 3 in parentheses tells us the charge. So we've got the iron 3 plus ion. Oxide comes from oxygen. And it is also in group 6A, just like sulfur. So its charge is going to be 2 minus. We need to make sure we've got the right number of each ion to balance out. If we have a positive 3 charge and a negative 2 charge, well, we can't just add those together. But if we have 2 of the iron, let me just write that again. If we have 2 of the iron and 3 of the oxygens, then that will balance out our charge. And if you use the cross method, you can easily see how you get there. So whichever method you choose, whether it's figuring it out with the math or just doing the cross method, as long as you get the right answer, it's all right. So how do we do with that one? What's your question? So this part we're looking at, this is the charge of the iron, the plus 3. And if we have 2 iron atoms, then the total charge would be 2 times a positive 3. And then likewise, the negative 2 is from the oxide ion, that's the charge. And that's if we have 3 oxygen atoms or ions. So we're looking at the total charge. You're welcome. So like I said, this takes practice. And if you've never done this before with naming and then writing chemical formulas, it's going to take a little more practice. So I'll double check and make sure that I posted that worksheet in the answer key. I'm pretty confident that I did, but I want to make sure it's there. So definitely use that to help you practice. We're still working on ionic compounds. So this is the last section where we're going to talk about ionic compounds. Then we've got one section on naming and writing chemical formulas for covalent compounds or molecular compounds. We're just going to be naming, and it's the same method as we were doing before. Only instead of figuring out the name by looking at the periodic table, you're going to figure out the name of the polyatomic ion by looking at this chart. You will get this chart with your exam. So you get the periodic table and you get the common polyatomic ions for naming. You don't have enough time to memorize these, and there's a lot of them to memorize. For naming, you write the metal first. Still the same rules in terms of using the Roman numeral if you have a transition metal. Then you write the name of the polyatomic ion. So for this first one, letter A, it would be magnesium. and then you find SO3, which is here. That's sulfite. And the name would be magnesium sulfite. Take a stab at B. You already know the first word is going to be magnesium. But find that SO4 on the chart and tell me the name of it. So I just highlighted it here. That's the sulfate ion. So that's magnesium sulfate. For C, we have a transition metal. We've got lead. So we're going to have to do the same thing that we were doing before, where you use the negative ion to figure out the charge for the positive ion. PO3 is phosphite. And its charge is -3. We have 2 of these. So there's the parentheses here, and then the 2 on the outside. This means that you have 2 of these ions. So for our charge, it's going to be 2 times -3, which is equal to -6. We've got 3 lead ions. And whatever their charge is, when we multiply it, we need to get +6. So what is the charge on the lead ion that we've got? It's got to be +2. 3 times +2 gives you 6. So the name is going to be lead 2 phosphite. So there's really nothing different about naming these compounds. It's just that you have to go to the chart to find the name of the polyatomic ion. Any questions about that? Yeah, I was going to say it's a big old silence, so I'm going to take that as a no. Now let's practice writing the formula from the name. I will tell you that carbonate is CO3 2-. I want you to try this one on your own first. Write a formula for potassium carbonate, knowing that the carbonate ion is CO3 2-. I'll give you about a minute to get started on it, and then I'll fill in the rest. So I'm going to get started here. Again, it's kind of hard to write chemical formulas in the chat box, So don't worry about it. We've got to write a formula for potassium carbonate. The carbonate ion is CO3 2-. We've got to worry about this potassium. We don't see any parentheses with the Roman numeral. So that means we should be able to just look at the periodic table and figure out the charge for this ion. It's a group 1A metal, so its charge is positive 1. Carbonate has a charge of -2. Well, if we just had one of each, that wouldn't work out. We need to have some more positive. That means that we need to have 2 potassium ions. Oops. So this would be our chemical formula. K2CO3. How did that go for everybody? Even if you didn't fully get to the answer yet, were you on your way? Or was it a complete ball of question mark? Ball of question mark right now. Well, I can talk it through again, and then we'll do another example. We have potassium carbonate. Carbonate you have to recognize as a polyatomic ion. So it's on that sheet. I told you that the carbonate ion is CO3 2-. So you can think of it as a whole unit, okay? We need to worry about the potassium. We need to figure out what its symbol is and what its ionic charge is. It's the first word, so that means it's going to be a metal. We find potassium on the periodic table. It's a group 1A metal. That means for the charge, it's just equal to the group number. It's got to be the one with the A after it. So the charge for the potassium ion is just positive 1. Now, if we were to only have one potassium ion and one carbonate ion, the charges we'd be adding would be +1 plus a -2. That doesn't give us 0. That gives us a negative number. So we have to add another potassium ion to balance out the charge. Now we've got +2 and -2. And that gives us 0. So if we're adding another potassium ion, we have to put a subscript of 2 to show that we've got 2 potassium ions. And then we've got 1 carbonate unit, which is CO3. So hopefully that helps a little bit, Jordan. But we're going to try another example. Yes, the CO3 is its own unit. So think about it as just one lump thing. You don't break it apart. So I'm going to tell you what each of these ions is, because I didn't have the space to put the chart up here. And then I want you to try to do these. So I'll give you 3 minutes to get started and figure out the correct formula for each of these. Because remember, your exam is going to be multiple choice. So being able to write it from scratch is great, but at least be able to pick out the right one if you see it. That's what we're going for here. So I will give you 3 minutes. Let's get started with number 1. What did we get? What's the correct formula? So it should be C. Aluminum is in group 3A. So its charge is 3+. So you need 3 of those nitrate ions to balance out the charge. What about number 2? I agree. So the copper has a charge of 2+. And you know that because of that Roman numeral there. To balance out the charge, you need 2 nitrate ions. How about number 3? Again, we're told the charge right away. Iron is 3+. Hydroxide is only 1-. So you've got to have 3 of those to balance out the charge. What about number 4? Should be A. Tin has that +4 charge. Hydroxide is 1-, so you need 4 of them to balance out the charge. So how do we feel about those? So like I said, there's practice for naming and writing chemical formulas. And there's the practice exam. So practice exam 2 is already posted in the course content folder. You'll get feedback. You'll see which answers are right and wrong. So with this, it just takes practice. Posted the YouTube videos the end of last week. It's Tuesday. So you might not be an expert, and that's okay. But as long as it's making sense and when you get something wrong, you understand why. If it's just, oh, it's wrong, no clue why, that's a bad place to be. But if you understand why, that means you can make corrections. We're going to take a 5-minute break here. We're going to break up the ionic compounds and the molecular compounds. Because from 6.5 forward, we're really focusing on molecular compounds. So take 5 minutes, and meet me back here at 12:44. Alrighty, so we're back from our break. At least I am. I can't see where you are. But we're going to get started because we still got a bit to go. Now we've got to cover molecular compounds. So molecular compounds are ones where you've got two nonmetals or more. But we're talking about nonmetals here. We're also talking about covalent bonds, which means sharing electrons. All that stuff before, we were talking about ionic compounds, which transfer electrons from the metal to the nonmetal. Here we're talking about nonmetals sharing electrons and forming a bond. We'll start with naming and chemical formulas. Naming is much easier, and writing the chemical formulas much easier than the ionic compounds. Let's take something that we all know, like water. Water is made of two nonmetals, so it is a molecular compound. To give water its proper name, you're going to first name the nonmetal that's first. So we've got hydrogen here. We have to indicate how many hydrogens we have. And if we have more than one, we have to use a prefix. This table 6.10 gives you the prefixes 1 through 10 that you're going to need to know. Most of these you've already encountered, so you will not get this on the exam. So the first word is dihydrogen. That means there's two hydrogen atoms. Next, we have to deal with the second element. The second element is named very similarly to naming the anion or the negative ions from ionic compounds. Only this time we will use a prefix. There is one oxygen atom here. The prefix for one is mono. Then you're going to use the first syllable of the word or the element, followed by IDE. Now, this is a little bit of a special case in terms of spelling. If you have two O's next to each other, you get rid of one of them. So it's monoxide. The other spelling thing you need to know is if you have an A and an O next to each other, you get rid of the A, and it's just pentoxide. But that's naming molecular formulas. You want to name the first element, and if there's more than one, you use a prefix. You always use a prefix for the second element, and then you name that element using the first syllable followed by IDE. So let's do a little practice. I want you to label each of these as ionic or covalent, And then just give the name for the covalent ones. So I'll give you 2 minutes to label each compound as ionic or covalent. And then just give me the names for the covalent compounds. So let's go through and just label them as ionic or covalent. So you can put an I for ionic or C for covalent. So what about A? Ionic or covalent? Think we might still be on break. Remember, if it's covalent, you're just going to have nonmetals. If it's ionic, you're going to have metal and nonmetals. So this first one, SO3, is covalent. What about B? Is that ionic or covalent? It's ionic. It's got a metal, which is barium, and then chlorine is a nonmetal. Now C, if you're not familiar with the polyatomic ions, may be a little bit tricky. But this is ionic. It's made of 2 different ions. Letter D is covalent. Now I'm going to go through and name the covalent molecules for you. We're only going to do A and D. We're going to name that first element, which is sulfur. There's only one, so we're done there. Now we've got to work on this O3 part. There are 3 oxygens, so we use the prefix tri, followed by the first syllable of oxygen, which is ox, and then it ends in IDE. So the name is sulfur trioxide. For D, we've got N2O4. The first element is nitrogen. We've got more than one, so we need to indicate how many with the prefix. So that's dinitrogen. We've got 4 oxygens, so we need to indicate that using a prefix. Yes. 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 The Roman numerals are only for metals. But for the molecular compounds, we're using the prefixes, like you see here. So we've got 2 nitrogens, no problem. 2 nitrogens, so that's dinitrogen. We've got 4 oxygens. That prefix is tetra. But with the whole spelling faux pas, you get rid of the A. As long as you know what the prefix is supposed to be, you'll be able to choose the right one on the exam. It's not a spelling exam. Thank goodness. So that's naming molecular compounds. Are there any additional questions on that? You'll also need to be able to choose whether or not a compound is ionic or covalent. And I could see there were some crickets there, which is why I helped you out. So you'll need to be able to pick that out too. So any questions on either of those topics? Then we'll keep moving forward. Now we're going to cover Lewis structures. We talked a bit about Lewis structures when it came to valence electrons and, doing it for a single atom. Now we're going to do it for molecules. So just as a reminder, the Lewis structure shows the valence electrons of all the atoms that are involved. It also shows where electrons are shared. Any place that you see a line, those are shared electrons. So that stands for 2 electrons that are shared between those 2 atoms. If there are any extra electrons that are not involved in a bond, they're drawn as lone pairs. So in this molecule ammonia, NH3, there's 1 bond to each of the 3 hydrogens, and nitrogen still has a lone pair. But how did we get to this? So we have to first remember how to draw Lewis structures of individual atoms. Nitrogen has 5 valence electrons. So we're going to draw dots around nitrogen until we get to 5. Placing 1 on each side, we've got 4. Now we've got to double up, 5. Hydrogen only has 1 electron. So that's the Lewis structure for hydrogen. We have 3 hydrogens. And anywhere you see 2 electrons like I'm circling here, that means you can replace it with a line. And don't forget that lone pair, because it's not bonded to anything. So that's how we go from the Lewis structure of the element to the Lewis structure of the whole molecule. We're going to do some practice, so don't worry. I'm going to walk you through another example and then check in on you. So here we're going to go through the formula for fluorine, which is F2, the fluorine molecule. Now, just as an aside, there are some molecules that appear as diatomic molecules. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. I talked about this in the video, but we didn't really have time to go over it today. But I'm just doing that as a plug. If you did not get a chance to watch the YouTube videos, there were 2. There's part 1 and part 2. Sorry. That's where I talk about that. So that is something you will need to know. But for now, just take my word for it. So if we want to draw the formula for F2, which is the fluorine molecule, you have to start with the individual atom of fluorine. Fluorine is in group 7A, which means it's got 7 valence electrons. So you're going to draw your Lewis structure for fluorine with 7 electrons. You go all the way around, you fill up, that's only 4. So then you have to pair up on 3 sides for 7 valence electrons. You put 2 of those next to each other, and you see where those 2 atoms can share electrons. Where they share electrons, you can draw a single bond. And make sure that you include all of these extra lone pairs. Because with the Lewis structure, we care about those lone pairs. They may be alone, but we care about them. So are there questions about that? It's kind of a refresher of Lewis structures in general, and then how to put them together. If not, just tell me that you're ready to move on. Okay. So we talked about single bonds, but some compounds have double bonds or triple bonds. If you have a double bond, you're sharing 2 pairs of electrons. So that means 4 electrons. One example of that would be the molecule carbon dioxide. There are 4 electrons shared between the carbon and each of the oxygens. So we represent that with 2 single lines, which is a double bond. You can also have a triple bond, and that's when you have 3 pairs of electrons, which is 6 electrons. So the bond between carbon and nitrogen can be a triple bond, and that's represented as 3 single lines. And we form these double and triple bonds when there aren't enough electrons to complete an octet. So we've got to kind of double them up and make them happy. But of course, there are exceptions to every rule. So we talked about the octet rule, where we're trying to get to 8 electrons through sharing. But some elements can do more or less. So hydrogen only requires 2 electrons for it to look like a noble gas. So when hydrogen is involved, it only needs 1 more electron to share and be happy. The nonmetals can form compounds with 10 or 12 valence electrons. So they can do some pretty funky stuff with their orbitals. You don't need to know that per se. Just understand that it can happen. So if you see a compound like SF6, don't freak out. It is not a typo. It's just that sulfur can do some weird things with its electrons. So let's try an example. We've got carbon tetrabromide. I'll give you 2 minutes to first write the formula for this molecule and then draw the Lewis structure. Now, obviously, you can't draw that in the chat, but I will draw it out for you and you can check your work. We're coming up close on time, so I'm not going to give you as much time as I usually do for drawing these things out. So I apologize. So I'll start by writing out what the chemical formula is for this molecule. Carbon tetrabromide. The way that it's named tells us that it's absolutely a molecular compound. Carbon, no prefixes, so that means we've got 1. We see bromide. That brome tells us bromine. And tetra says that there are 4 of them. So this molecule is CBr4. Carbon is in group 4A, which means it's got 4 valence electrons. Bromine is in 7A, so it's got 7 valence electrons. The Lewis structure for carbon would just have 1 dot on all the sides. The one for bromine would look exactly like the one for fluorine. 2 dots on all sides except for 1. Now we've got to put these together. We've got 4 of the bromines and only 1 of the carbons. So the atom that you have the fewest number of, you're going to put in the center. We've got the fewest number of carbons, 1 versus 4. So we'll put that in the center. Now we've got to put our bromines all the way around. Everywhere that you see 2 dots like this, left one off. All of those pairs that I circled will become lines for single bonds. And of course, make sure that you have all of your lone pairs. So how do we do for that? Okay. Yeah, part of this is kind of a refresher. That's Lewis structures in a nutshell. Electronegativity. We're talking still about molecular compounds mainly. And we're also going to talk about bond polarity. So electronegativity just tells you the affinity that an atom has for an electron. So if you're very electronegative, then you've got a very high affinity for an electron. There's a trend that goes along with this. On the periodic table, and we're talking about the representative elements here, electronegativity as you go from the top of a group to the bottom of a group decreases. As you go across a period from left to right, it increases. And if you think about it in terms of, in contrast to metallic character, which we talked about, this trend makes sense. I will leave that to you when you're studying because that is part of chapter 5 for periodic trends. So if that statement doesn't make sense to you after you've done your studying, feel free to send me a message or stop by office hours. Anyhow, we're looking at electronegativity. And that's simply how much does that atom want an electron? We can use the electronegativity of the different atoms to figure out the type of bond between 2 atoms. You can have nonpolar, that's nonpolar covalent, polar covalent, and ionic. If the difference between the electronegativity of the 2 atoms involved in this bond is 0.4 or less, it's going to be nonpolar. If the difference between the two atoms is 0.5 to 1.8, it's going to be polar covalent. Higher than 1.8 or higher, we're looking at ionic. Now, there is a little bit of gray area that I address in the YouTube video, but this gives you the nuts and bolts of it. So this right here, this last bullet point, is kind of the caveat between polar covalent and ionic. I'm not going to go over that specifically here. I just want you to get the idea that there's different types of bonds, and those bonds are dependent upon the difference in electronegativity between the two atoms. So to demonstrate that point visually, I like this table. With nonpolar covalent bonds, you're sharing electrons equally. With polar covalent bonds, you're still sharing, but it's not shared equally. One of the atoms has a higher electronegativity value than the other. So you can see that they're still connected, and this is just kind of the electron sharing. Ionic bonds, there is no sharing. We've got transfer of electrons, so we're making ions. So you can see there's no connection here. So hopefully that's kind of a visual of the different bond types. Does this concept make sense? Okay, so now I'm going to show you what I mean by electronegativity difference. So you will get information regarding electronegativity. You do not have to memorize this table. So you can use the difference to identify the bond type. For A, we've got chlorine bonded to chlorine. So 3.0 is the electronegativity, and you have the same thing bonded to itself. So that's a 0. So it's going to be nonpolar and covalent. For B, we're still looking at chlorine, but now we're looking at hydrogen as well. .9 puts us into the range of polar covalent. So is it clear what's expected of you when we talk about electronegativity difference? Okay. And again, I apologize. Chapter 6 is kind of big. That's why we didn't have any time for exam review. But naming is usually the hardest part for students, which is why we focused on that one so much. So we've got a couple of more things to cover. We're going to talk about the shape and polarity of molecules, and then the types of interactions that molecules can have with each other. And then we're done. For shapes, we're going to use what's called the VSEPR theory. That's the valence shell electron pair repulsion theory. You may have heard that if you took chemistry in high school, particularly AP chemistry. And all this theory does is describe the orientation of the electron groups around a central atom. An electron group can be a lone pair, or it can be a bonded atom. And this theory states that electron groups are arranged as far apart as possible around the central atom. And that makes sense because electrons are negatively charged, and like charges don't want to be around each other. So you're not going to have groups of electrons being really close. That negative charge is going to repel them, and they're going to want to be as far away from each other as possible while still being connected to the central atom. Because of that, specific shapes can be determined by the number of atoms and the number of lone pairs attached to the central atom. So we're going to go over that. This table, 6.17, is what you need to know in terms of the shapes. It tells you the number of electron groups, which I told you is bonded atoms and lone pairs. When it comes to the molecular shape, we only care about the number of bonded atoms. The lone pairs will influence where those bonded atoms are in space, but we don't include them when we're looking at the molecular shape. So if you have something that's linear, you're going to have one central atom and then two bonded atoms. So an example of that would be carbon dioxide. And that's linear. If you have three bonded atoms and no lone pairs, it's trigonal planar, so it's kind of like a peace sign. They're all 120 degrees apart. Trigonal planar, now we're introducing a lone pair in addition to the two bonded atoms. So that lone pair is going to push these two groups closer together. And that's going to be bent. So you can't see the influence of that lone pair, but it's still having the same influence like another bonded atom. So the angle's still the same, the bond angle, but the name of the molecular shape is different because instead of three bonded atoms, we've only got two. Then we've got tetrahedral, which is four bonded atoms. So like CH4. Then you've got trigonal pyramidal, which has a lone pair and three bonded atoms. So again, the lone pairs matter in terms of the placement of the bonded atoms, but it's only the bonded atoms that tell you the molecular shape. The final shape is another bent shape, and that's where you have two lone pairs and two bonded atoms. So you're squishing those atoms that are bonded together, so it's bent, but it's not as far apart as the two bonded atoms and one lone pair. So I just went through those quickly just to try to give you an idea of the difference in the molecular shape. And now I'm going to go through a practice problem so you can see how we can go from the formula to the shape. Then I'll check in with you. We have the formula CCl4. The first thing you're going to do is draw the Lewis structure. And that's going to tell you the number of bonded atoms and the number of lone pairs, because that's the information we need in order to assign a shape. Carbon has 4 valence electrons. And chlorine has 7. So when we draw this, we have to make sure to put our single lines in all of these lone pairs. Now keep in mind, when we talk about the number of bonded atoms and the number of lone pairs, we're talking about the central atom, which in this case is carbon. So how many bonded atoms are there in this shape, or in this structure, excuse me? How many bonded atoms do we have? We've got 4. There are 4 atoms connected to the carbon. You can tell the number of bonded atoms just by the number of bonds you have. So however many single lines you have, that's how many you've got. So we've got 4 bonded atoms. The carbon doesn't have any lone pairs. We don't care about the lone pairs on the chlorine. We only care about the carbon. And since we've got 4 bonded atoms and no lone pairs, our molecule shape is going to be tetrahedral. So you have to figure out this part for your molecule in order to assign a shape. And I would recommend using flashcards to help you learn the shapes and the number of bonded atoms and lone pairs associated with each. I'm going to press forward so we can at least get through the rest. And then if you have questions, you can ask after class, and you can always come to office hours or set something up with me. So we've got to talk about polarity of molecules. We talked about the polarity of bonds, nonpolar covalent, polar covalent, and ionic. Well, if we take those bonds and arrange them in space using these different shapes, depending on the type of bond, we may have a polar or a nonpolar molecule. I've taken the information on the slides and condensed it down into a table. For nonpolar, there are 3 different shapes and conditions that you can have a nonpolar molecule. The first is that you just have all nonpolar bonds. So if you've got all nonpolar bonds, then it's a nonpolar molecule. And an example of that would be oxygen gas or hydrogen gas. You can also have a nonpolar molecule if you have polar bonds that cancel each other out. So in the case of carbon dioxide, we have 2 polar bonds. Again, you need to watch the YouTube video because we don't have time to draw dipoles and talk about all that. But we've got a partial positive on the carbon and a partial negative on the oxygen because the oxygen is more electronegative than the carbon. But we've also got the same thing going in the opposite direction. So that balances each other out, and we've got a nonpolar molecule. The other way that happens is with the tetrahedral shape, where you can have polar bonds, like in the case of CCl4 that we just drew. And because you've got opposites canceling each other out, you've still got a nonpolar molecule. So I'm not going to take the time to go through all of these different arrangements for polar, but you will need to understand these. So please watch the video and then come back to this table. This table will help you with your homework. We don't have time to do all of these learning checks, so I'm going to run through one for you, and I'll make sure that the answers are included for the others. So we need to label a molecule as polar or nonpolar. The first place you start is by looking at the bond type and figuring out what kind of bond you have. You use the electronegativity for that. 0.7 tells you that you've got polar covalent bonds. But that's not the end. We also need to figure out the geometry. Phosphorus has 5 valence electrons, and bromine has 7. We're going to arrange each of these around. And assign a shape. We've got 3 bonded atoms and 1 lone pair. That means our molecular shape is going to be trigonal pyramidal. With polar covalent bonds in this shape, this is going to be a polar molecule. And so you can use that chart that I gave you on the other slide to figure that out. I'm going to give you the answers for this one. And then we've got intermolecular forces. Again, I'm sorry, this is really fast. But this table summarizes everything that you need to know. The forces between 2 molecules, so if you had 2 molecules of water or 2 molecules of hydrogen gas, that's what we're talking about. Hydrogen bonds, dipole-dipole interactions, and dispersion forces you will need to know. Dispersion forces, we're talking about 2 of the same nonmetals. Dipole-dipole, 2 different nonmetals. And hydrogen bonding is a hydrogen plus fluorine, oxygen, or nitrogen. And you can remember that as having FON with hydrogen bonds, which is really corny. The strength of those goes from the weakest is dispersion forces, followed by dipole-dipole and the hydrogen bond. After that, ionic bonds. Those are the strongest. In terms of melting point, because you'll need to know that too. Low melting point for the weaker force. High melting point for the stronger force. I will complete this example for you and put it in the notes. These are all the reminders that I have for you. There's a practice exam posted on Blackboard, and it's got some Chapter 6 problems for you to do. It will tell you what the correct answer is if you get it wrong, so that you can figure out what you know and what you don't know. The exam will be available Wednesday, which is tomorrow, through Friday. So you've got time to figure out Chapter 6 material. And I have office hours tomorrow from 2 to 4. If that time doesn't work for you, if you have a second now, stay behind and you can send me a chat message, set something up. Otherwise, send me a message in course messages as soon as possible to set up a time. You have Mastering Chemistry that's due on Sunday. It will help you study Chapter 6. So use it. Do the homework. And there's no chapter check-in because that would just be evil. So with that, that's all I got. I'm sorry it was fast at the end, but chapter 6 is really big. So please watch the 2 YouTube videos and make sure you get it. I'll take any questions you have. Otherwise, you're free to go.